Okay, I am going to officially start class now. This is, again, CSE 373, Analysis of Algorithms. I think this is our second lecture. First of all, let's start with, are there any questions about logistics or something like that? Were people able to successfully turn in the daily problem?
Yes.
Okay, any questions about the daily problem or how we, not what it was, that I'm going to go through in a few, a little later. But people should have been able to turn that in. Any other logistical questions about the course?
This is a question about the daily problem. Is there anything we're supposed to name the file we upload in particular, or does it not matter?
I don't think it matters what name you upload the daily problem with. Okay, so if that's what, do that.
Okay, thank you.
There's a question about, will the daily problem submission only be open in that window? The answer is yes. My goal, so the daily problem, I think it is important that this is about trying to keep you live with the class. And so I synchronize the daily problems to be turned in at the beginning of class. Again, in a normal world, we do this by people physically turning in papers. But now we are, dealing with this. There's, again, some of these discussions about, oh, did I submit the right thing or not? These are probably best off left for Piazza. Okay, hopefully people got things submitted. If there's a big thing, there's a question here about, is it okay if we type the response on Blackboard instead of uploading a problem? Actually, this is a question for Yi Min. The way that you're planning on grading these things, would that mess things up or don't know?
It should be fine.
Okay, so the claim is that's fine if you want. Okay, any other questions about daily problems or any other logistics? There's a question about, should we do textbook readings between lectures? I think reading the textbook is a very good thing. It's one reason I wrote it. And if you look at the syllabus, at the lecture schedule for the semester, I give readings for what the pages of the book are corresponding to each lecture. So I think it is generally a good thing to read the book before class. Some people are before class book readers. Some people are after class book readers. Some people are, don't read the book. That I think is a bad thing. So you use your judgment how you're supposed to deal with it. Any other questions?
Professor, so if we got enrolled into the class a little bit late, and we didn't know about the daily problem question, could we submit like only for today? Could we mail you the solution?
So the question is, can there be an exception because for some extremely worthy reason you couldn't turn in the daily problem? The answer is no. The daily problems are a rigid thing. They have to be turned in the time window. If you miss one because something weird happened, you forgot, then that is a very small hit to your grade. So don't worry about that. But so the important thing though is I like this to be a mechanical thing. This is the ritual of you coming to class, and that's what the daily problems are about.
So where are the questions posted about the daily problems in the syllabus?
Where are the questions? So if you go to my website, okay, www.cs.stonybrook.edu/tilde-skeena, SKIENA/373, you will see a posting there with what the daily problem is for every class of the semester. Okay, I will hopefully stay in sync with that. And if I don't, at some point I may issue a correction. But that's where you go for it. So I recommend everybody get that and use that from now on. Any questions? Okay, so at this point, I'd like to start the lecture for real. Usually I do the daily problem right at the beginning of class. I really like to do it that way. today, because the daily problem is about finding counterexamples at things. There was one more of these kind of exercises of how do we design algorithms or look for daily problem, for counterexamples. I'd kind of like to go over that. So this is a job called the movie star scheduling problem. That you are suppose you are a movie star, and they will pay you $1 million for every movie you're in. Maybe you're Brad Pitt or something like this. And your agent, okay, comes to you with a list of possible projects. If you look on the screen, we see there's probably about 10 possible movies there, okay? And the x-axis represents the calendar, represents time. And each potential movie, there is a time when the shooting starts and there's a time when shooting ends. And so for you to take a job, you can't take two jobs that overlap each other, because then you have to be in two places at one time and you can't do it, okay? So in this particular case, how many movies, what's the most number of movies that somebody could, our movie star could take if this is the schedule of possible things? Does anybody have a proposal how many movies they can do? I see someone saying 4, less than or equal to 4. Again, less than or equal to 4 is easy. Just don't do anything. Declare, go on strike. But what set of 4 movies can I do here? I claim I can do, if I am correct, I can be able to do discrete math. If I could do discrete math and halting state, okay, and the programming challenges and calculated bets, this is a set of 4 movies that I could do and nothing overlaps. Does everybody agree with that? Is there any alternative solutions that have 4 things involved? Does anyone see any other choices? I mean, someone say I could star in Steiner's tree instead of halting state. That seems like one possible choice. I guess I could star in the president's algorist and Steiner's tree. That would also be another pair. So there can be more than one possible optimal solution. But in this case, the optimal solution is a size 4. Any questions? So how, if I give you a set of problems, I give you a set of movies, what is the, and each movie is represented by an interval on the line, a start time and an end time. How do I find what is the maximum number of movies I can do simultaneously? Does anyone have a proposal for an algorithm? Okay. Anyone with a voice? I'm hearing some.
Does it allow the overlapping?
What do you say? Allow overlapping? What does that mean?
Means like the maximum amount of movies they can do, but does it allow like 2 movies to overlap?
No,
or
it does not allow 2 movies to overlap. I can't be in 2 places at the same time. Okay, if I could be in multiple places at the same time, I will take all of them. Okay. Okay, so I'm hearing some people say, oh, I have an idea. What if I take, and this is again, basically the movie star scheduling problem. I'm giving you a set of n intervals. I want to know what is the largest subset of non-overlapping intervals that can be selected, and I want an algorithm for it. And some people are saying smallest job, do the shortest job first. You're telling me if I'm going to be paid $1 million for doing a movie, I'll be darned if I'm going to spend my time doing a big, long movie. I might as well get paid $1 million for doing the shortest job. And if I do the shortest job, then that probably leaves the most other time for doing other things. That's the idea behind the shortest job first algorithm. Any ideas of why that can't work? Okay, can anyone give me a counterexample? Well, actually, I'll give it on my slide just because I'm doing this thing. Here is an example of why doing the shortest job okay, is not necessarily the right thing. Does everybody see that? The shortest job is this one. If I do the shortest one, I am blocking out two other jobs that I could do, right? If I always take the shortest job and keep taking the shortest job that doesn't intersect something, I might get stuck and only end up with half as many jobs as I like, as are possible.
I have a question about this example. So let's say the shortest job still like overlap. Let's say if the shortest job still overlap with one of the bigger job, is it gonna be problem? Like let's say I choose two shortest job and both of them overlap each other.
If the two shortest jobs overlap each other, I mean, again, if there was another job that looked like this, could I do both this one and this one? No, I can only do one of them. So the shortest job first algorithm, heuristic, I didn't really go through the thing. I'm going to take what is the shortest remaining job, delete that job and anything that intersects it, that overlaps it, and then keep going. What's the shortest remaining job? And I'm going to keep doing this until, I run out of jobs. That's the shortest job first. I should have convinced you by now that that can't be correct. Any other ideas for an algorithm that is correct?
I was thinking of possibly constructing a n-ary tree, kind of a tree of, if I pick this movie, what can I pick next, and then finding the height of that tree.
Okay, so what I'm hearing is something that to me says do an exhaustive search. If there are n jobs, how many different possible subsets of jobs are there? Does anybody know? If I have n jobs, okay, how many different subsets of jobs are there?
2 to the n.
I'm seeing n factorial, but that is wrong. I am hearing 2 to the n, and that sounds right. Suppose, let's say I have two jobs here. They're jobs A and B. How many subsets are there? There's the subset of A, the subset of B, the subset of A and B, and the subset of nothing. That's 4. If I add another job, okay, I am doubling the number of subsets. Basically, I have all the subsets without the last job I added, of which there have to be 2 to the n minus 1. And I have all the subsets with the job that I just added. And that's got to be 2 to the n minus 1. 2 to the n minus 1 plus 2 to the n minus 1 is 2 to the n. Okay? But 2 to the n is an exponential thing. So I don't want to enumerate all the jobs. So someone who says, yes, try all subsets, or build a tree that will enumerate all subsets. You're correct, but you are slow. And that's a problem if there's a faster algorithm. Any other ideas on this?
So I kind of have a partial solution, just because this reminds me very similar to some problems we did in AMS 301 involving coloring graphs. And I was thinking, like, maybe I'm just thinking, throwing this idea out there, maybe someone can finish it up. But basically, like, maybe if you generate a graph where vertices that connect at an edge are overlapping, and then like you would try to basically
so we could build a graph where as a vertex, a network where there's a vertex for every every segment. There's an edge if two segments intersect, and then we can make this a question on graphs. Turns out the magic word for this name, the name of this problem on general graphs, is called independent set. And we'll talk about it late in the semester. But actually, just like finding the minimum number of colors, that actually is a hard problem. So yes, I can say, make this a graph problem, and which makes it a general graph problem, and find an independent set. That doesn't get me where I want. Okay, let me just show you one other thing that doesn't get me where you want. Another heuristic might have been, why don't we do the first job, that the job that starts earliest? I'm not getting any money. I can't earn any money until the earliest movie is. So in this case, it would be going back to this thing. If we look at this example, I couldn't be earning money until the president's algorist. Okay, maybe what I should do is keep taking this job. Then once that's done, I can't start working productively till I have the next job that starts. I can't work there productively until the next job that starts. I can't work productively until the next job that starts. On this example, that finds the optimal solution of 4, right? When would it be a mistake, though, to take the first job? Can anybody think of an example where...
The first job is too big.
Okay, I have the exact case. I did kind of show that there. If the first job was the movie War and Peace, which takes forever to film, if you start working on that, you have to give up all the red ones in order to do that. This is a counterexample to earliest job first. So how can we do this correctly? We haven't seen an algorithm that is both correct and efficient. Okay? Here is an interesting idea, though, that for one that is correct and efficient. What if we take the job that has the earliest completion date and then delete it and everything that's over it, and then repeat with the next one that has the earliest completion date? So if, let's just make some segments here. Here I've got some segments, and here I got another one, and here I've got these. Which segment should I do? Okay, I believe this is it. The earliest one to complete is this one. Does everybody see that? I would take this segment. I would then have to kill this segment and kill this segment because it overlapped it. Then, which is the earliest job to complete? I am going to claim it's this one, and that would cause this one to get killed. Now, which is the earliest job to complete? It looks like it's this one. Okay? And I would kill this one and that one. This algorithm would come up with a solution of 3. Does everybody get the idea of what earliest to complete is? Why is that one correct? Does anybody have any idea? Give me an idea why that idea is correct. Well, I'm going to give you an argument based on an idea called proof by contradiction that I think you guys have seen. Suppose it isn't, okay? If so, then I could be making a mistake by taking this first job, okay? My question is, how could I be making a mistake, okay? Well, there's going to be 2 possibilities. One is the real optimal solution used one of the jobs that intersected it, okay? Why would I be better off, though, if I had a solution, that optimal solution that used the jobs that intersected the first to complete? Why can I remove that job and replace it with the first to complete? Does anybody see that? Seeing nothing. I'm hearing nothing. Okay.
It's because you still have the same options available.
Does everybody see that if instead of taking this, I took this, because this was the first to complete, I have every option available still, and maybe even a few more. It's possible there were a lot of other jobs that ended over there, right? So my claim is, of all of these jobs, if you're going to pick any of them, you might as well pick the first one. Does everybody agree with that?
Yes.
And what if you tell me that the optimal solution included none of these jobs? Okay, it wasn't including the first to complete or anybody that intersected it. How do I know that that can't be the optimal solution? Suppose you tell me, no, 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 this and this is the optimal solution. Why do I know that that can't be the optimal solution?
Well, by definition, we should be able to add the next one that we are not considering.
Because when I put this job, basically, if I'm not having the first to complete or the ones that intersected, it should be clear that the solution so far does not intersect the first one to complete. If so, I could add first one to complete to it, and it will still do even better, okay? So my claim is I never go wrong by picking the first job to complete. And this is now an algorithm that is both fast and correct. How many people see that? Or any questions about that? So this is the kind of cleverness we like in an algorithm world, okay? We have an algorithm that for a problem that in fact is now, it's clear it's quite efficient, okay? What's this thing going to do? It's going to spin around taking jobs. This while loop is going to take a total of at most n jobs, so this is going to go around at most n time. If we have the jobs sorted by completion date, what are we going to do? We're going to take the first job with a completion date, and then know that we know what the completion date is. We're now going to take a look at the job with the next completion date. And if it intersected the one we had, then if its starting point was before the last thing we had, there's an intersection. If not, there isn't. I claim by scanning through this would be an efficient algorithm. Any questions? Any questions about this? It should be inspiring that here we have a fast algorithm for solving this problem exactly, whereas before all we had were heuristics or a brute force search. Any questions about that? Okay. Any questions? Okay. I'd like to now get into the second lecture, which I'm hoping my machine will do. I know your screen has turned blank, correct? Give me a second here. I've been finding my device is very slow for changing slides, but hopefully we won't get jammed like we did last time. Okay, so I want to talk now start talking about the big O notation. And in particular, I want to start with the problem of the day. What was the problem of the day? The problem of the day said that you are considering the knapsack problem. What is the knapsack problem? The knapsack problem says you're given a collection of integers, okay, and a target number. And you want to find a subset of the integers that you're given that adds up to the target. And so out of 1, 2, 5, 9, 10, my claim is that there is a subset that adds up to the target. Does anybody, what subset adds up to 22? Does anybody have a sense of which numbers add up to 22?
10, 9, 1, 2.
I'm seeing 1, 2, 9, and 10, right? Does everybody agree that that adds up to 22? But there's no way to have it add up to, 23. Can anybody figure out why this is called the knapsack problem?
I think it's because you have like different objects that you put in your bag, and that's knapsack came from that bag.
Right. So let's say you're robbing a jewelry store and you've got a knapsack that has a certain capacity. You want to try to fill that knapsack as full as possible so that you can get as much loot before running out. This is asking, if you have objects of different sizes, is there a way to pick a subset of sizes that are exactly the same size as the knapsack? Okay? So what is the problem of the day? The problem of the day says, find a counterexample to the following algorithms for Knapsack, okay? Suppose I am given my set S, okay, and I've got my target equal to T. Suppose I try putting the elements into the knapsack from left to right, okay? Can anybody give me a counterexample to this algorithm? The algorithm is fill it in from left to right, okay? A counterexample is what? You're going to give me a selection of numbers to put into the weights of things to put in that I can choose from, and you give me a target T such that we make the that this algorithm is going to give us the wrong answer.
Let's say the set is 1, 2, 3, and the target is 4.
Okay, 1, 2, 3, and the target is 4. Now, why is that a counterexample? What's the first fit algorithm going to do? It's going to say, item number 1, does it fit in my target thing that has a capacity of 4? Yeah. Item number 2, does it fit, item of weight 2, do you fit in my thing that has a remaining capacity of 4 minus 1 equals 3? Yeah. Now I've got weight 3 in the knapsack, okay? If I now, can I stick the item of weight 3 in the knapsack?
No.
No, okay? And if so, you know, so that's going to tell me that the most I can fit in the knapsack is 3, but you're telling me no, if you used a different algorithm, you would have seen that you could fit, you could have gotten 4 in there. But this algorithm doesn't work. That's a counterexample. Okay? Any questions about that? Do people see why that's a counterexample? Okay, this is enough to kill that. This one example is enough to kill that strategy. Can anybody give me an example that will kill the algorithm where we put the items in from smallest weight to largest weight? Can anybody kill that heuristic?
I guess the same example works, same counterexample works for the second case too.
Okay, in fact, if you notice, this particular case, the knapsack was sorted from smallest to biggest. Does everybody see that? And so because it was sorted from smallest to biggest, the exact same thing is going to happen. And you're going to put things of weight 3 in there instead of things of weight 1. Does everybody see that?
Yes.
Now, any questions? Now, when I'm designing so this one's bad too, that much was clearly pretty clear. Is there a simpler, okay, example? Again, when I think about designing counterexamples, I really like them to be as simple as is humanly possible. Can anybody come up with an even simpler example that breaks both of these heuristics? Okay, empty set. I don't know what empty set
so
does.
like if you
Okay.
have 1 and 2, and you
What if my set was 1 and 2?
And T was 2.
Does everybody see that in this case, it's simpler? Instead of having 3 items, I have, what you call it? I have only 2 items. And instead of me having to count to a big number like 4, here I only have to count to a number like 2. Does everybody see that? The simpler you make the counterexample, the easier it is to understand and to convince someone of. Okay? What about the last case? Is there an S and a T that you can give me such that putting them elements in from largest to smallest breaks?
I think the first one, like 1, 2, 3, works for this case also.
First of all, is 1, 2, 3 going to break that heuristic if I, put them in from largest to smallest? I'm going to claim no.
No.
What's going to happen in this case? I am now going to start by taking the element 3
and then it'll
Does
skip
3
2
fit in the
because that won't.
knapsack? Yeah. Now I'm going to try to put 2 in the knapsack. Is there room for 2?
No.
No. There's 1 element. Oh, look, the next one is 1. Is there room for it?
Yep.
On that example, okay, going from biggest to smallest, putting the elements in from largest to smallest gives me the right answer. Does everybody see that?
Yes.
Does anybody have a counterexample for this one?
If you simplify that set to just 2, 3, then sorry, no, never mind. That doesn't.
Okay,
that
I'm
doesn't
seeing a couple things on the chat. One question is, do the elements of the subset have to be less than or equal to the target? Well, certainly if they're bigger than the target, they're going to be no use to us. If we come into if we go into the jewelry store we're robbing, and we have a small knapsack, if there's a car in there, we can't steal the car. Okay, but if we're allowing it to be equal size, if there's one item that's the exact size of the the knapsack, certainly that's a legal thing. Okay, so what else do I see? I guess the smallest example I see on the chat right now is 2, 3, 4 for being S, and T equal to 5. So what's going to happen? Well, we're going to grab, okay, we're going to grab the example of size, item of size 4. And once we do that, we have only room for, we don't have room for the item of size 3, and we don't have room for the item of size 2. So we would say that most we can put in there is 4, but these 2 items add up to be 5. So yes, that is a counterexample of this, okay? And if we do that, then we're in deal. We're right, okay? Somebody else I'm seeing in here is saying something like, if my subset was 3 and 2, and my target was 2, is that a counterexample to this? No, because I try the 3, it doesn't fit. I try the 2, it does fit, okay? So in that case, this would not be a counterexample, okay? But this is a counterexample. The one up top, 2, 3, 4, is a counterexample for the biggest to smallest insertion. Any question about that? This is the kind of thing that you guys are going to have to be able to do. Many times when you design an algorithm, it's going to be wrong, okay? And I can say that's true for most of the people in this class. Most of the algorithms you'll design are wrong. Being able to recognize it, see where you propose an idea, being able to tell when it's wrong, okay? And moving on is a critical part of algorithm design. Any questions? Okay. And there's questions of, can the knapsack problem have negative integers or something like that? When you're trying to make a counterexample, maybe you use weird things like negative numbers, if that'll help. But again, I like the simplest example here. Is there any item in the jewelry store that weighs -1 pound? Okay. So if I can get away without that, I think that's a better way to think about for counterexamples. Any questions? Okay, good. Okay, I'd like to now start kind of a new unit, not a unit. I want us to now start talking about the big O notation. Now, I'm going to guess that many of you have seen the big O notation in some other classes, and I am going to guess that many of you don't like it. How many people here like it? How many people here don't like the big O notation? Anybody? Now I'm seeing people who don't like it, okay? Well, there's going to be a reason why we're going to talk about the big O, and it really relates to the fact that we want to design algorithms that will we want to find a way to analyze algorithms in a way that doesn't worry about computers. Okay, yeah, I see that there's a problem with my slide. This I'm sorry about. My slides in all their full beauty and glory are on the web. So if someone really wants to follow that, that's where we can go. But okay. So what is what we would like to be able to do is to analyze algorithms in a machine-independent way. And to do that, we've got to kind of come up with a theoretical model of a computer, okay? And the model of the computer that I am going to be interested in is something called the RAM model of computing. RAM is for random access machine. And what is it that the random access machine does? Okay, it says that a computer has an instruction set, and every instruction takes 1 unit of time. Okay, 1 millisecond, 1 computron, whatever you want to call the smallest unit of computation. If that's true, we can say how much time an algorithm takes by counting how many steps it had. When we count the number of steps, we are not going to count a loop as a simple operation, because a loop goes around as many times as the value of n in that loop. Okay? So it's not fair to say I have a loop that goes from 1 to 1 billion to say that takes 1 step. No, each time through the loop might take 1 step. But all told, if it's going around from 1 to 1 billion, it's going to do at least 1 billion steps. Okay? And although it costs constant time to call a subroutine, the work done in the subroutine has to be counted. So when you call some subroutine that does quicksort, okay, or sorts your numbers, you've got to pay the time that the subroutine takes to do the sorting. Okay, it's not that you can say that it doesn't cost anything. The other thing we're going to assume about our computers is that every time we access the memory to read or write, it takes 1 step. Okay, those are our 3 assumptions. Are those assumptions reasonable? Is it true that, let's say, a multiplication of 2 numbers takes as much time for your machine as the addition of 2 numbers? Not quite, not really. Are there, I guess this one I think I trust, that in fact that everyone will agree that subroutine calls are not simple operations. Is it true that in real computers, every memory access takes 1 step?
Can you explain this one? Like, how come? I mean, how this will take 1 step accessing a memory?
So external memory is maybe what you're talking about. That somehow that if you access it on a disk, accessing location on a disk takes much longer. Or accessing something in a cache is much faster than accessing it in main memory. So this is a very, very simplified model of the computer, okay? So that we can measure the running time of an algorithm by counting the number of steps. It's not a very accurate, it's not a thoroughly accurate model, but it's simple to work with and it has a lot of truth to it. And models that are simple and easy to work with are great things, okay? Who here believes that the Earth is flat? Do we have any flat earthers in this class? Okay. I don't think that we have flat earthers. But the model that the Earth is flat is a very, very useful thing and often the right way to think about it. When you go to the store to buy sneakers, do you check to see if at the bottom of your sneakers are curved and beveled to match the circumference of the Earth? The answer is no. You're assuming that your world is flat, okay? When you are when you're getting a piece of furniture on the scale of a piece of furniture or even a house, the property that you have on your, if you have a housing property, the earth is flat. Maybe if you're building a suspension bridge like the Verrazano Bridge, okay, then maybe you need to worry about the fact that the earth is curved. But does everybody see that over a large amount of range, the flat earth model is a right way to reason about the world? The RAM model is over the range of stuff that I'm interested in, the right way to reason about the world. Any question about flat earth, the roundness of the earth, or about models, or the RAM model in particular? Okay, good.
So RAM model is only for like a small computations or like small
Is the RAM model only for small computations? The answer is actually no. That's not really the analogy. That's probably the wrong analogy then. The RAM model is to give you a certain gross level of accuracy, a gross idea of what's going to happen. Now, it might be, if we think about it, if we're neglecting the fact that accessing a disk is 1,000 times slower than accessing main memory, our model might be off in terms of a prediction of how many steps it takes, might be off by a factor of 1,000. 1,000 times the right answer is not necessarily a bad guess, okay? So it turns out that what we're going to be using this model for is trying to get the big order of magnitude. How does the running time of an algorithm depend on the size of the data? And we'll see if we're off by a factor of 1,000, that's going to be uninteresting to us. Any questions? Okay, Okay. So let me get into this idea of complexity. And when we talk about the big O, maybe what is confusing to people is that there are two different ideas we're going to be using here. There's going to be, first of all, what function are we interested in getting out of our analysis? What are we trying to analyze? And the second is, how do we specify the running time in a way that it is easy, or how do we specify the value of that function in terms of a way that it's easy to work with? So first, let's think about when we're analyzing algorithms, what are we interested in? Okay, when we say that we want to know what the running time of an algorithm is. I claim we can think about any algorithm as in the following way. If you take any algorithm and you try it at all possible inputs in the world, any possible input file that's legal with that problem, you're going to get a graph that looks something like this. The x-axis is what's telling us what the problem size is, which is typically n. And the y-axis is going to be the number of steps that the algorithm uses, which is the running time of the algorithm, f of n. Every dot here represents one input, okay, of that size. So if we were looking at a sorting problem, this would represent, every dot would be if we look at every dot in this column, is going to represent one of the possible 4-element sorting problems. How many possible sorting problems are there on 4 elements? Well, it could be the items are in order, 1, 2, 3, 4. Could be the last 2 are mixed up. It could be any arrangement of the 4 things. There are, in fact, 4 factorial, or 24 different, sorting instances on 4 things. Each one of them here is represented by a dot. One of those examples is going to be the easiest to sort, the one that we sorted with the fewest comparisons. Maybe it was 1, 2, 3, 4. Another one was going to be the one that we required the most work for our algorithm. Maybe that was 4, 3, 2, 1. Okay? So this defines, if you think of what I'm doing, I'm relating the examples to every instance is a dot. What's interesting is that there are 3 functions that go through these dots that we're interested in. If we did plotted through the lowest dot at each case, for each n, we've got the red curve, which is describing the best case complexity of the algorithm. If that's, how many steps would it take if we always got lucky with what they gave us? The worst case would be the blue function. What is it if we always got unlucky with the example that they gave us? And the average case, that's the green one, would be what if they picked the examples at random? And that therefore, what would be the expected time that it would take if they gave us random examples? Worst case means they're giving us we're unluckiest, they're giving us the hardest example. Best case is they're always giving us the easiest example. Average case means they're picking the examples at random. Any questions? So the function, when we talk about the worst case complexity, what we are talking about is the curve that goes through the worst case. Any questions about that? Okay. Now, what do we know? Okay, there is best case, worst case, and average case complexity. As I said, best case is the one that describes the time it takes on the easiest example. Worst case is the time that it took on the hardest example. Average case was the average. The important thing is that each one of these complexities gives us a function where the time is a function of n. Any questions about that? Good. So which of these measures of an algorithm? So every algorithm has a function as a function of n that measures its worst case performance, its best case performance, and its average case performance. Which is the one that will tell us the most meaningful stuff? Okay? And I'd like to say, if I want to reason on the value of a lottery ticket, what is the right way to think about the value of a lottery ticket? One way you might say with the value of a lottery ticket, the best thing that can happen is I am going to win $100 million. Okay? Is that the right way to think about a lottery ticket? Well, it's possible you win $1 million, but $100 million, but you won't. Okay? I've been buying lottery tickets. You don't win. I can guarantee you don't win. I can't guarantee it, but I can be pretty darn sure. What is the worst case thing that happens when you buy a lottery ticket? Does anybody have an idea? What's the worst thing that can happen to you when you buy a lottery ticket?
You don't win the lottery?
You lose, okay? Or you lose the dollar you spent on the lottery. Okay? Now, what is the expected value of a lottery ticket? Okay? Is it 0? It's almost 0, but not 0, right? And it's probably pretty hard to compute what the expected value actually is. So what's interesting about this? If you tell me, if you're trying to decide should you bet on lotteries or not, the worst case complexity gives you a pretty darn good analysis, even though it was very, very simple to do. Okay? And so it works the same way with algorithms, that if you give it an algorithm, trying to figure out the best case running time is usually pretty meaningless. If you have an algorithm that on some example took very little time, but almost always takes a lot of time, you learn nothing from looking at the best case, okay? If you look at the worst case, it turns out to be fairly easy to analyze, okay? And gives you a good picture of what it's doing. So in general in this class, we are going to be talking about, in general, we are going to be asking for worst case analysis, okay, unless I tell you otherwise. In this class, we're going to do a little bit of analysis of randomized algorithms. Randomized algorithms are a very interesting class of algorithms that are becoming more important and that you need to think in terms of average case complexity. But the reason we care about worst case analysis is because, because it's easier to do and it gives you a good picture of what the algorithm's really about. Any questions about that? Okay, good. Now we'll get into the dreaded big O notation. And the important thing to see about analyzing algorithms or any other function, if you have a very, very complicated function, it can be hard to talk about a very, very complicated function, okay? You know, complicated functions like the black one here wiggle around a lot, okay? And might not have a nice algebraic form and might be complicated to think about. It is often easier to talk about a function, not in terms of the function itself, but an upper bound of the function or a lower bound of the function, okay? This is kind of why we're going to be dealing with it. The worst case running time of a function, of an algorithm, is this complicated function representing the maximum number of steps over all examples. The details are complicated, okay? What we're going to rather do is to talk in terms of, instead of describing exactly what that black function is, we'd be better off talking about what the upper bound is and what the lower bound is. And that's what brings us into this asymptotic notation, where we talk about the big O, the big omega, and the big theta. Any questions? Okay, so let's talk about what these things mean. Okay, the big O, saying that G of n is big O of f of n. That means that f of n, big O, is for upper bound. It means that there is some constant c such that c times f of n is always an upper bound of your function. The omega function says that there is some constant times f of n such that that this is a lower bound on g of n. And saying that g of n is theta of f of n means that f of n is both an upper bound and a lower bound of g of n. If I know that I've got a world where here is my function g of n, here is an upper bound, here is a lower bound. If the upper bound and lower bound are both of the same kind of function, then we have a pretty tight window where g of n has to live. And in our dream is, if we want to know the behavior of g of n, if we can say that g of n is f of n of a function that we know about, is theta of a function we can reason about, that's a good thing. Any questions? I know this is where people are starting to get murky, but let's bring this down. Oh,
I had a really quick
not
question.
Hold on. That was terrible. I lost it. Okay, now I'm in big trouble. Hold on. Give me a second. Hopefully it will come back. I assume you guys aren't seeing this, right? Okay, bing. Okay, got it. Let's say I go down here. So the important way to see the big O notation is in terms of upper bounds and lower bounds, okay, and what you want. Here, actually, I think I reversed the role of f of n and g of n in these pictures, so don't get too confused. We're interested in the black function, the function in black, okay? The function in black is maybe the running time of an algorithm. Maybe it's the wealth of Jeff Bezos. Let's say we want to figure out what the wealth of Jeff Bezos is. What do we know about Jeff Bezos? He's the guy who owns Amazon, right? Is he getting richer with time? Yes, but does he occasionally have a bad day in the stock market? I will claim that as a function of time, this is the dollars that Jeff Bezos is worth, right? If you want to plot and talk about that exact function, okay, that is hard to, not very interesting. But if I instead drew a function like this, suppose this was the function 3 to the n, and this was the function 2 to the n. What would this mean? Generally speaking, Jeff Bezos' income every year more than doubles. That's what the bottom lower bound is, right? The lower bound would say if n is the number of years, Jeff Bezos' wealth will be growing faster than doubling every year, but slower than tripling every year. Does everybody see what that kind of is? If we can talk about his wealth in terms of simple functions, we can reason about it. If we have to talk about this complicated thing, we can't. So what is the big O, the big omega, and the big theta? Well, we're going to be interested in, and a big O is the upper bound. Big O means we've got an upper bound. This is the big O. We say that f of n here is big O of g of n, okay, in this figure. If f of n is less than or equal to some constant c times g of n, that's the big O such case. The second one is the omega case. Why? For a large enough n, beyond a large enough n, c times g of n is a lower bound of f of n. It's always less than or equal to it. So this is telling us that f of n is less than or equal to c times g of n. It is omega of g of n. And if we have a world where there is one constant c1 times g of n that is an upper bound, and another constant c2 times g of n that is a lower bound, then we say that it is theta of g of n. Any questions about that?
For theta of g of n, g of n would have to be the same degree function for both big
Right,
O
so
and
we're
omega,
interested,
right?
g of n and g of n are the same function. Okay, so maybe this would mean that, let's say g of n was n squared. So what would it mean if this thing was n squared, if it was theta of n squared? What would that mean? Okay, well, what do we know about C1 and C2? Is C1 in this case going to be bigger, greater than C2, less than C2, or the same as C2? What is the relationship between C1 and C2? Okay, which is bigger? So everyone's saying C1 is bigger than C2. It has to be because that's what makes it an upper bound, right? Any questions? Okay, let's try this again. Let's now
So
try
I got
the
a quick question.
Question, yes.
So can we think about it as in the upper bound is like the worst case and the lower bound is like the best case?
Okay, is the upper bound the worst case? Look, the answer is no. And this is why one of the things that people get confused by here. I said there are two ideas we're learning about today. We are learning about ways of counting the complexity of an algorithm, which we said were best case, worst case, and average case. And we are learning a language to talk about functions, which is the big O notation. The big O notation does not necessarily only apply to best case or worst case thing. Let's look back, remember, think back to poor Jeff Bezos over here. He has an upper bound. He has a lower bound. Is there any best or worst case here? Okay. I guess you might think.
I'm just saying, like, in the
so
context of
recognize
like
that when
the
we're talking about
runtime.
the big O no stuff, we're talking about a function. The big O stuff, when we talk about is something big O of something or omega or theta, we are talking about properties of functions. Okay, we're not talking about meanings. Okay, once you know what the function it means, okay, then what the function means, then you can interpret, okay, any particular value as in some way. When Jeff Bezos hits near 3 to the n, he had a good year. When Jeff Bezos doubles his money in a year, he's crying. Okay, it's not the worst thing that can happen to him, if this is in fact upper and lower bounds. Any questions about that? So what are the formal? It's important that people try to understand the formal definitions of these things. Okay, and it's not that hard. And when I work on a problem with the big O, okay, until you get fluent with it, you got to always go back to the definition. What does it mean when I say that a function f of n is big O of g of n? What do I mean when I say that the worst case running time of n is O of n squared? What does it mean? It means that there is some constant c and some constant n naught, such that for all n greater than n naught, okay, f of n is always less than or equal to c times g of n. That's what it means to be an upper, that g of n is an upper bound of f of n. Any questions of how we read this? The n greater than n naught, okay, is referring to the fact that we don't care about small values. We don't care about how rich Jeff Bezos was when he was 13. He wasn't Jeff Bezos then. He became Jeff Bezos when he founded Amazon, right? Okay. And we want to know from then on what happened. What is the second function? The omega. We say that f of n, let's say the worst case running time, is omega of g of n if there is a constant n naught and c such that for all n greater than n naught, that's the same thing that we had before. I might as well even try to write it neater. Okay, here we're saying though that f of n is, okay, is greater than or equal to c times g of n. This was the upper bound. This is the lower bound. And we say that f of n is theta of g of n if there are positive constants n naught, c1, and c2, such that f of n is always less than or equal to c1 g of n and greater than or equal to c2 g of n. Any questions? Do people kind of get the definitions? It's important to try to understand the definitions in this business. Okay? Any questions? I'm a little sorry about my handwriting, but frankly, it comes out much better on here than on the board, so you're very lucky. Any questions? Okay. Let's look at some examples. If we want to work with the big O, let's look at some examples. Why is, let's say we have a function here, a complicated function like 3n squared minus 100n plus 6. Why do I say that it is order n squared? It's big O of n squared. Why is it order n squared?
Because the highest degree is 2 over here.
You're saying because the highest degree is 2, you're reasoning on a level beyond my definition. I can't think that fast.
Because n
The
squared.
reason it is because, okay, I'm going to claim that there is some constant times n squared such that that constant c times n squared is bigger than f of n. Isn't that what I wanted my big O to be? What value of c is going to work here? For what value of c is c times n squared greater than 3n squared minus 100 minus 6 plus 6? Does anybody have a value of c that I could use here to make that true?
4.
I'm seeing 4. 4 is a good thing. Is 4 times n squared always going to be bigger than 3n squared minus 100 minus 6?
Yeah.
You say, yeah, well, it's not always true. What about n equals 0? 4 times 0, is that greater than or equal to 6? Does everybody agree that for n equals 0, that's not true? But I think it's true that by the time I get that for all n greater than 1, 4 times n squared is going to be bigger than, is that true?
Yeah. No,
Is
no, no,
4
no,
times
no.
n squared going to
No,
be
no, no.
bigger than 3n squared minus 100 plus 6?
No, not really.
Not for 1. For 1, that would be is 4. No, that's not going to work. What about 2? 2 squared times n, and 2, if n is equal to 2. 2 times 2 is 4, 16. This is going to be 3 times 4, that's 12 plus 6. That's not good enough. But I think there is going to be a point where this is going to work. Does anybody see a point where it's going to work? What's the value of n that this is going to be good for?
N greater than or equal to 3?
If I pick my c equal to be 4, 4n squared is going to be what? That can be thought of as n squared plus 3n squared. Does everybody agree that n squared is equal to n squared plus 3n squared is equal to 4n squared?
Yeah.
Well, the 3n squared part is going to be as big as that, so that I'm not worried about. Minus 100n, well, that's never going to make this side bigger, is it? So I'm not worried about that. Suppose I pick an n such that n squared is bigger than 6. What would be an n for that? Okay. What would be an n for which n squared is bigger than 6? I think 3, right? So I think that so long as n is greater than 3, if c is equal to 4, does everybody see that for all n greater than 3, this equality is going to be hold. This equality is going to hold. Okay? And that's what proves the big O. Any questions about that? What about, is there any value of n? Is it true that 3n squared plus this thing, is that big O of n cubed? Is n cubed an upper bound of this function? Well, one way to reason about that is that n cubed is going to be, bigger than n squared. So if n squared is an upper bound of this function on the left, then n cubed certainly is going to be. Okay? That's one way to reason about it. But if we go to the definition, you need to give me a constant such that c times n squared is always bigger than this, okay, for all n greater than n naught. It should be clear that, there exists some n such that 0.01 times n cubed is always going to be greater than or equal to this. Can anybody give me a value of n naught such that 0, 1, n cubed is always greater than 3n squared minus 100n plus 6. Does anyone want to propose an n naught for that? Well, we knew that for, for the previous case, if c was equal to 4, n naught of 3 would be done. This 0.01 times n cubed could be written as 0.01 times n squared. Does everybody kind of see that? That's equal to n cubed. What value of n is going to make this equal to 1?
10.
That's 1 out of 100. Is that right? By the time we got to n equals 100, this thing is going to be 1, and for larger n, it's going to beat up on that constant. So certainly 100 times the old bound for n greater than 400. This is certainly going to be true. Any questions about that? And the last one here, okay, at least on this slide.
I have a question.
Is it possible that, that n is an upper bound of n squared? Is there any constant times n such that c times n is going to be bigger than 3n squared? Okay. Is there any value of c such that c times n is always going to be bigger than 3n squared? What if I say c is equal to 1 billion? Something really big. Boom. That's a big c. Is there a value of n such that c times n is, in fact, going to always be bigger than this? And the answer is no. If we take the square root of this thing, that's like halving the number of digits. What would that be? By the time that n equals 10,000, 10,000 times 10,000 is bigger than this c. Does everybody see that? So 10,000 times 10,000, okay, is going to be bigger than what we are looking at. There exists an n, or maybe even better. Actually, I said that kind of wrong. Under what condition, if c is equal to 1 million, what do I have? C is equal to 100. Well, let's make it 1 billion. If c is equal to 1 billion, what is the relationship here where this is going to be true? When is 3n squared going to beat 1 billion times n? Well, by the time n equals 1 billion, this is going to be 1 billion times 1 billion, and this is going to be 3 times 1 billion and 1 billion. Does everybody see that once you fix a constant, no matter how big it is, this side is going to be bigger for a large enough n? So there is no constant that will do the job, and this is not big O of that. Any questions about that?
I have a question, like, it's pretty much, I'm not sure if it's the summary of what we just learned. It's like, for upper bound, we can go, even if the function is, let's say, the highest value for function is, let's say, n square. We can get big O notation of n cube, and it will still be a big O notation for that function.
Okay, so because the big O is an upper bound, if in fact one way that you want to think about it, you're trying to think about it, you're saying find the biggest term on this side. When the polynomial on this side is this side is greater than or equal to the degree of this, then the big O holds, and here the degree is 1. That's n to the 1. In this case, the degree here is not larger than that. Is here it's larger, so big O holds, big O holds. Here it's not true. That's kind of what you're saying.
Yeah.
Okay, fair enough. Let's look quickly at the big omega case. Is it true that 3n squared and change Is that big O theta of n squared? This means a lower bound. Is there some constant such that a constant times n squared is always less than or equal to 3n squared? What would be a good constant here? What would be a value of c such that c times n squared is always less than 3 times n squared? 1, I see 1. I'm seeing c less than 3, 2.99. I guess if it's less than or equal to, the 3 is good. Okay? So any constant that is greater than 0, okay, and less than 3 is going to work here. Okay? Because there is some change here, it's going to vary what the cutoff where we're guaranteed we're going to beat it. Okay? But it should be clear that there is a small constant we can multiply n squared by, so that this is always less than 3n squared and change. Is there a constant that we can multiply n by, so that c times n is always going to be less than 3n squared? What would be a constant for that? That's for this bottom case down here. This is true. Okay? Is 3n squared theta omega of n? Well, no matter how big a constant you pick here, maybe make it billions. Okay? By the time we got to n equal to c, this side is going to be bigger. Okay? So yes, this relationship holds. But there is no constant you can multiply n cubed by, so that it is always less than n squared. Actually, is there any constant you can multiply c by n cubed by so that it's less than n squared? Think about it. Is there any value of c such that c times n cubed is less than n squared?
A negative number?
0 or a negative number. We don't allow c to be 0 or a negative number. Okay? What this basically says is that as far as what are the lower bounds on this? N squared is a lower bound, n is a lower bound, but n cubed is not a lower bound. Okay? And when we look at the big theta, okay, we know that something is big theta. This is big theta, this is in big theta of that. If this is an upper bound and a lower bound, meaning that both the big O and the big omega held. There exists constants times n squared, such that c1 times n squared is bigger than this, and c2 of n squared is smaller than this. So this is true for the theta. But in this case, the big O relationship holds because this is an upper bound, but it's not a lower bound. In this case, n is a lower bound of this, but not an upper bound. So the omega holds, but not the O, okay? And so the theta doesn't hold. Any questions about that? Okay? It's important to me that you guys come to understand with this C constant and the N naught, why these functions satisfy these relationships. Okay? Any questions about that? This is what the big O notation means. It gives us a language for talking about upper and lower bounds of things. And we're going to use that for our favorite function, which happens to be usually the worst case running time of an algorithm. Any questions about that? Any questions about anything big O related?
I had a question.
Yes.
If you were to find, like, if we were told to find, like, the n naught value for which, like, after, like, eventually, like our big O function was always greater than the actual function, does that have to be like a really tight value or like the exact value, or can it be any n naught value?
Okay, we are interested when you're proving that something is big O of something else. You are demonstrating there exists some n naught and some c that will do the job, such that beyond, okay, for all n greater than n naught, okay, c times this, okay, is an upper bound of that. That's what you're trying to do. You don't really get points for having a very tight n naught, okay, and you don't really get points for having a small c. You need to have a pair of n naught and c such that for all n greater than this, it's going to hold, okay, for that given c.
Got it.
Okay? So you're just trying to prove to me that at some point, this is going to be an upper bound. That's what you're trying to do here. Okay? And once you can do this in your head, you can believe that that pair is going to exist without doing any fancy algebra. Okay? But that's kind of what you need to do. You need to really convince me whether it's big O or not. You've got to show me an n naught and a c where it's obvious that that relationship is always going to hold. It's always going to be an upper bound for n greater than n naught. Any questions here? If not, I'm going to thank you for your attention. I want you to think about, this is one of the most painful points in the semester. So I want you guys to go and make sure you read on the, this is a good time to read in the book to make sure you understand it. It's a great time to do the daily problem and start looking at maybe some of the homework problems to make sure that you understand this. Okay? Good luck with it. Have a good weekend, and I will see you guys next week. Okay? Great.